Hello everyone, this is Chongchong from Professor Jian Yu's group. Here I'm going to show you our recent work on ambient measurement of heterogeneous ozone oxidation rate of 3 unsaturated fatty acids in an urban environment. Cooking emission is an important source of ambient organic aerosols, especially in urban cities. It can contribute to a significant fraction of total OA. Cooking profiles are dominated by the organics, especially saturated and unsaturated long-chain fatty acids. The left figure shows their chemical structures. Among them, the unsaturated fatty acids, which contain one or multiple double bonds, are highly reactive and can react with atmospheric oxidants such as ozone. This reaction, called the heterogeneous reaction, will change the particle compositions, altering their chemical and physical properties. Oleic acid has been selected as a model compound to study the heterogeneous reaction. The left figure shows the reaction mechanism. The gas phase ozone will diffuse into the particles and attack the double bond on the oleic acid molecules, and this will form the primary ozonide, and this ozonide is very unstable, will rapidly decompose and forming different cyanide acid. Previous oleic acid reaction mechanism studies are mainly based on the laboratory studies. We know that the conditions in the lab experiment are quite different compared with real atmospheric environment. For example, in lab experiment, they often use very high ozone concentrations to initiate the reaction, while in ambient situation, ozone levels are much lower. And also in the lab experiment, the simulated simple aerosol matrix is used to mimic ambient condition, but the simplified matrix cannot represent ambient complicated aerosol matrix, and still there and large variations exist in the laboratory estimate oleic acid lifetime, ranging from minutes to days. So the purpose of this study is try to quantify the oleic acid decay rate in real atmospheric environment. And this study will fill the gap between the laboratory study and the field observation. The 3-week field campaign was conducted at an urban site in Shanghai, and the sampling site is a typical urban site influenced by a wide mixture of emissions and evolutions. Specifically, the bi-hour saturated and unsaturated fatty acids were measured by TAG instrument. The right two figure shows the backward trajectory cluster analysis during the whole sampling period. We can see that the whole campaign was influenced by both regional and local air mass. Specifically, the first sampling subperiod was influenced by regional air mass, with cluster 4 and 1 dominate. Under this condition, we observed higher O2C ratios and higher ozone concentrations, while in the last sampling subperiod, it was mainly dominated by cluster 2 and 3, representing the influence from local air mass. Lower O2C ratios were observed, and also the ozone concentration are much lower. Another background information about this sampling site is that from the concurrent source apportionment study, it showed that cooking emission contribute to 15% of the total OA, and is an important source contributing to the organic aerosols measured. And this slide shows the diurnal variation of the individual cooking molecules. The top panel is the diurnal variation of their concentrations, while the figure B is the diurnal variation of 3 unsaturated fatty acids normalized by the stearic acid. We can see that the concentration shows highest value at 7 p.m., which is around dinner time, suggesting the influence from local cooking activities. The normalized concentration can eliminate the interference from the dilutions. So the decreasing trend after the dinner time is mainly due to the continued loss of the unsaturated fatty acid due to the chemical degradation. We select the normalized unsaturated fatty acid concentration data in the nighttime to calculate the rate constant. We assume that there is no cooking emission during the nighttime period, and the reference compound stearic acid is non-reactive toward the oxidants. Another assumption is that the cooking particle composition will not change, and this can be attributed to the relatively stable meteorological conditions within each night. So we can use the exponential function to fit the ambient data and obtain k-value represent the pseudo first-order decay rate, and it can be expressed as the second-order rate constant multiplied by the oxidant concentrations. We calculate the day-by-day decay rate for the 3 unsaturated fatty acids, and the whole data can be divided into 2 scenarios. Scenario 1, which represents influence from the regional air mass, shown in the left panel as an example. 17 out of 22 nice data belong to this case. Under this condition, we can obtain a constant k-value during the whole time period using one-step exponential fitting, and obtained k-value can represent the decay for partially aged or aged OA under the regional air mass influence. Another scenario which represents the influence on the local air mass. Under this condition, we observe that the rate constant changed during the whole time period. Thus, we adopt two-step exponential fitting to obtain two rate constants, with the initial rate constant K1 obtained for the first 4 hours, representing the faster decay for fresh OA, while the later rate constant K2 obtained for the last 6 hours, representing the slower decay for partially aged OA. This slide shows the estimate rate constant from ambient measurement. Figure A shows the box plot of the rate constant for individual compounds under the different scenarios. We can see that for all the compounds, it shows that the initial rate constant K1 is much higher than K2. This can be explained by the high surface concentration of unsaturated fatty acid and higher ozone solubility in the fresh OA, which leads to much faster initial reactions. While figure B shows a correlation between the rate constant with the nighttime ozone concentration. The good correlation between the K and K2 versus the ozone concentration suggests that the ozone is the major oxidant responsible for the unsaturated fatty acid decay, as expressed by the previous equation. The K is the second-order reaction rate multiplied by the oxidant concentration. As we have determined the rate constant for 3 different compounds, we can compare their relative rate constant, as shown in Figure C. We can see that the rate constant of Elaidic acid is 0.6 times of that of oleic acid, and this can be attributed to the different chemical structures due to the cis and trans configuration of the carbon-carbon double bond. While compare the rate constant for linoleic acid with the oleic acid, we can see that the rate constant of linoleic acid is about 1.4 times of oleic acid. If we only look at the chemical structure difference, we would think that the rate constant of linoleic acid should be 2 times of oleic acid because it has 2 double bonds. But the observation from the ambient data shows that both chemical structure and other factors such as diffusion limits will influence the heterogeneous reaction rate. We then compare the estimated lifetime of oleic acid in our work compared with the previous chamber studies. From our result, It shows that the lifetime of oleic acid is about 44 minutes under the ozone level of 100 ppb, and this result is in agreement with the highlighted 3 studies, but much longer than the results obtained for pure oleic acid particles and liquid solutions. And also the lifetime is much shorter compared with the result obtained for solid mixtures and oleic acid particles from these 2 studies. And this haphazard agreement between our result and the previous chamber studies suggests the importance to obtain more ambient measurement-derived kinetic data to increase our understanding about this reaction mechanism. This work has been published in the Geophysical Research Letters recently. If you are interested into more detail about this work, you can go to the original paper for further information. And that's all. Thank you.